Autonomous vehicles, what are believed to be a key stepping stone in the improvement of our transport system. But is the development of this field fully satisfactory? Well, to answer that question, it's key to understand subsections needed for a desirable level of autonomy. These key sections involve perceiving depth, detecting objects, and detecting the state of objects, which means working out which way an object is about to move in the future. My name is Andrew, and I'm going to talk you through my project, which aims to improve the methods of depth using a method called perspective projection. And could you please save all your questions to the end of this presentation? So how do autonomous vehicles actually work? Well, a lot of these use either LiDAR or radar sensors, where LiDAR sensors are omnidirectional sensors typically placed on top of the vehicle and work by using laser beams, whereas radar sensors are placed on each side of the car typically and work using radio waves. An example LiDAR sensor can be shown on the left-hand side of the slide here, and a radar sensor is shown on the right-hand side. However, car companies such as Tesla have now opted to do depth perception entirely using cameras. This method is more complex and requires more computational power, although it is much more cost-effective. But how do we use cameras to perceive depth? Well, to answer that question, we can compare cameras to our own eyes, except we as humans perceive depth using both our eyes using a method called triangulation. However, a single camera cannot use this method. Similar to how if we went and covered one of our own eyes, which you can do with me, and held up an object in front of you, it's hard to perceive how far away it is. With triangulation methods off limits, companies have looked to use artificial intelligence to fill this gap and have used neural networks. These networks work by training over a large subset of data images, with an example image shown in the top half of the slide. These are then compared against ground truth data, which is in the form of a depth map. An example depth map is shown in the lower half of the slide. For each iteration, the image, when it's compared with the other image, it improves the model until it slowly becomes better and better until you can just pass it an image and it will correctly predict a new depth map for that image. This method is very good, and it will give a decent prediction to every pixel within the image. But how can it be improved? Well, I've looked to improve on this by using perspective projection to give a more valid prediction to a certain range of pixels within the image, being the objects within the image. Now, I'm sure you're wondering what actually is perspective projection. Well, it's the concept of how objects appear smaller as they get further away, as shown by the train tracks in the slide, where they start off wide as they are close, and then they slowly get shorter and shorter as they get further away. Our brains can also identify which of the tennis balls in the image is the closest and which is the furthest away. As I'm sure if you give a quick look, your brain will identify that the one that is the furthest away is the one on the very far left. So, to actually apply this method to find the depth of cars within an image, an equation had to be found that could link the size of that car with its depth. These equations are shown on the right, which proves that the depth of the car is inversely proportional to its width. Now, if we want to visualize this data, we can plot it on a graph, as shown in the image. Now all that is left to do is to find a method which you can pass the width of a car in and get the depth back out. This can be fulfilled by using something called a linear regression neural network. However, the first step in this means that the data has to be linear, which can be fulfilled by plotting depth versus the inverse width, as shown in the graph. To train this model, we first have to find a large subset of data points, where each data point is a depth value and an inverse width value. To first try and calculate the width of cars within an image, we need to first identify where they are in the image. A method used to do this is using a neural network model called DTR. Some examples of an input video and the DTR output for the video is shown in the slide, where DTR will predict where each car is within that image and place a bounding box over that car. With each car in an image are now identified, a method can now be used to find the approximate size of each car. The method chosen for this is a 3D bounding box model, where the car is approximated a 3D bounding box which can be used to give a width, height, and length of the car. These estimated dimensions of cars only roughly represent their actual dimensions. However, the width more accurately represents the width of a car. Also, the width of cars is very similar over a range of cars. Therefore, the width of these boxes has been used to identify the apparent size of cars within an image. Taking the inverse of this width, we have our first point in the data points that we need to plot to make a full graph for linear regression. With the data points for width of cars now found, we can look to find the depth to each car in the image. We can do this by using a ground truth depth map. Here in the depth map, each pixel represents the depth to that pixel, such that if we want to find the depth to the car, we need to first find the pixels that represent the car and then find an average of the depth of each pixels in that car. Now, to find the pixels for the car, we can use a segmentation model, and I've chosen to use the DTR segmentation model, which uses a neural network. Results using this segmentation model are shown in the slide, with the input image video and the output segmentation video. The output of the segmentation model gives us an array of segmentation masks. So if we take each segmentation mask for a car and take the ground truth depth data and then average this to get a depth, we can then use that value as our depth point in our graph. Using this, if we take each depth value we've now found and its corresponding inverse width value, we can store them together as a tuple. And then we can do this for a number of images and keep saving these data points until we've got a large number of tuples in a dataset. For the project, I've run this over a number of images, which total 7,518 cars, which gives you that many number of data points. We can then plot them on a graph, which forms the graph as shown here. Then, if we use the linear regression model, it tries to fit a line that best fits that data set. And then you can then store that line to predict data in the future. With our model now saved, which is the equivalent of saving the equation of the line, we can now use it to predict the depth of cars within a normal image. We can do this by finding the width of the car and plotting it along the graph and finding its corresponding depth as shown in this slide.